Hello and welcome to Math, Minecraft to Computers, episode I18, Binary Coded Decimals. Now over here I built a simple display just to show a lot of bits, and what we're going to talk about today are two things. What is a word and what is binary coded decimal? Okay, so here we are. It's something that I've built to show a number of bits, and you can see that I've got 4 bits set here, and it's just simply a switch with the light. I can turn these on or off, just turn the light on. Now, a word is the number of bits, once again, that you can transfer between the CPU and the memory in one clock cycle or in one chunk. So a 4-bit processor, for instance, would be able to move this number of bits, which is 4, at a given time, back and forth between the CPU and actually memory. CPUs can be complicated and they have different sort of things inside, but we actually define a word by how they can interact with external data sources such as memory. So a 4-bit processor such as the Intel 4004 or the Intel 4040, for instance, which were made for calculators, actually used 4 bits. And there's a reason for this. The number that you can store, obviously in 4 bits, is 16 different numbers. That's 2 to the 4th, so it's 0 through 15. In 3 bits, you can store 8 numbers. That would be 0 through 7. But if you want to do actual base 10, you have to add 1 more bit. And they used a process called binary coded decimal, which we'll get into in just a little bit of what it is to store numbers in the calculator. And then, of course, we move up and we double that, and we get to the 8-bit processor, which shows you now instead of doing 4 at a time, we can do 8. And that gives us a number between 0 and 255. So the largest value you'll see in there is 255, which is 256 individual values. There were quite a few of these. These were very popular in early home computers, such as the Motorola 6809, which was in the TRS-80 color computer. It was in a lot of the coin-op video games like Joust. Quite a few different systems used that. And then another one is the MOS 6502, which was a popular one as well. It was in the Commodore 64. All the Atari 8-bit computers, the Atari Lynx. In fact, it was actually one of the biggest selling chips of all time because it was in the Atari 2600 video game console way back in there when it was the first console that you plugged into your TV. And not only that, but it was also a version of it was in the Nintendo Entertainment System. It still used the 6502. So there were millions and millions of these made. But beyond that, we have to step up, and we then move into the 16-bit. Right here, we doubled the size. And now you can see it's quite a bit more. We're moving a lot more. And of course, the numbers that we can store here are 0 to 65,535, which is actually 64K. That is 64 times 1024, which is 64K. So those 8-bit computers very often had what's known as double the size memory bus. So the memory bus was 16 bits, allowing it to see 64K, even though it could only do math and move 8 bits at a time between memory and the processor. So 16-bit processors came in. That was, for instance, the 8086, and we move forward until we get to 32-bit processors. And 32-bit, just double that again, puts us down to this area about right here. So here's a 32-bit processor, and it can store a number between 0 and 4,294,967,295. So decent sized chunk there, but you couldn't keep track of the number of people in the world, and that it's still too small. But it is a decent amount of data. But we're going to do to modern computers now are using what's called a 64-bit processor, and we double that again, and we move all the way down here. It'll take us a while to get there because 64-bit is a lot of data. And here we are. We have arrived at the 64-bit processor. It stores very large numbers. Okay, so the range of numbers it can store is between 0 and 18 quintillion, 446 quadrillion, 744 trillion, 73 billion, 709,551,615. So there you go. Say that fast 3 times. So a 64-bit processor, as you can see, I'm going to look down here. It's a lot of data that it's moving. All the way back there, you can see that light on there. That is the 32-bit processor right there. And so it's got double that. It's a lot of data, and it's very large numbers. So now we're pretty serious. Now, are there 128-bit processors? Yeah, they are, and certainly the 64-bit processors, even in the computers that we're using today, have 128-bit registers. But in general, they only move 64 bits back and forth between memory. So while there are some experimental 128-bit CPUs, in reality, this is so much data, this is kind of where it stops. We may eventually get there, but 64 will let us get a lot of space. Now, this number also on this back side here, this maximum number that you see, is the amount of bytes that a processor can access if its address bus is the same size as a word. So that's a lot of memory there. And if we even go back to the 32-bit, which is going to take a while to get there, you can see that a 32-bit processor has this, which is 4 gigabytes of RAM. So they were limited to 4 gigabytes of RAM without some sort of extensions to be able to allow them to do more. That is it. Now we're going to talk about binary coded decimal. And binary coded decimal is very simple, using 4 bits, like these 4 right here, in a 4-bit processor to represent a base 10 number. So this is 1, because we've actually put in a binary number as 1. But for instance, this would be 7. If I turn all of those in, it's 4, 5, 6, 7, and that's 7. But if I want to go to 8 and 9, I need to add 1 more bit. So it required 4 bits. So this then, of course, would be 8, and then 9 would be, excuse me, this is 8 here, and then you turn this on, and you get 9. So that's actually how you did it. There were anything beyond that, for instance 10, we don't have a digit for 10. We use 2 digits in base 10 to do 10. So those are invalid, but that's how binary coded decimal worked. It stored a base 10 digit in 4 bits. And then it actually did math that way. So to kind of see an example of this, we'll go over to our construct where we built the display over here. And you can see we have a number sitting on it right now. So we'll figure out what this might be in BCD. So the way we do that is we take 4 bits at a time. So we have these right 4 bits and we have these left 4 bits, and we store a number in there. So this number is 1. We don't have a 2. We have a 4. We don't have an 8. So this is 4 plus 1, which is 5. So I'll put that up here on this digit. So these 4 bits represent this number, and then these 4 bits over here are going to represent this number. So let me put a 5 on here. And then over here on this side, if we look at these 4 bits, we have to add what they are. It's a 1 plus a 2 plus a 4, and we don't have an 8. So what is that? That is, of course, 7. So in BCD, we have a 5 on this side and a 7 on this side, so that is 75. Let's do a couple more to make sure we have this. So, all right, we'll leave it at that. What do I have now? I look at these 4 bits over here. I have a 1 and a 2, which makes this a 3. And over here, I have an 8 and a 1, which makes this a 9. So what is our number? 93. We have a 9 on this side, so that's this digit, and we have a 3 on this side, which is that digit. So that is exactly how binary coded decimal works. You use 4 bits to represent a number. A byte can do 2 digits, and this is actually how those 4-bit processors process numbers. You can even do BCD. The 6502 had a BCD mode where it did binary coded decimal as well. Okay, that is it for MMC I18 binary coded decimal. Hope you enjoyed. Keep on learning. Give me some likes and subscribes if you want more. Roy, out.